Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last week, where we had written a few equations on how the torque can potentially be expressed. And we had of course seen that this entire calculation is extremely sensitive, or rather depends on the exact construction of the induction motor, right? So we had followed, if you look, we had used this particular image to determine how force will be produced. So we had used this concept of saying that if we consider the ideal case in which force is only tangential to the circumference of the rotor, then in that case we are only considering the rotational torque which is produced, and therefore we can express the rotational torque in this form, that is equal to torque which is equal to the number of rotor bars, or rather force multiplied by the radius. So we had said this was the case. Now, we had initially said that this method of computation, though seems perfectly reasonable because it's based after all on the basic laws of physics, is not really used. And the reason I gave is that it is so very dependent on all the construction details, right? Now, if you are looking to develop a detailed induction motor model with all construction details, and this is quite often used in modern electrical machine analysis tools, right? So there are modern tools which do allow you to actually put in machine details and therefore determine how the machine will behave, right? Now, of course, they also use some very advanced concepts like finite element analysis and several other nonlinear techniques, those which I cannot even cover because I don't even know what those are. But in general, these kind of software do take in construction details, and they do some form of computation very similar to this. Now, for our purpose, this kind of computation is largely not really suitable because we do not want to go into so much construction detail just to be able to develop a simulation model of an induction motor, right? In our case, we have an induction motor, we have the rating, we have the voltage rating, we have the power rating, therefore we have the current rating, we have the rated speed, number of poles, and that's it. Typically, that is all we need to simulate an induction motor. And I have already shown you this in the previous case. That is, if we know, using just the no-load test and block rotor test, if we know the voltage rating and the power rating of a motor, we can calculate the entire equivalent circuit of an induction motor. It is possible. So therefore, we don't really need to go into construction details in such a manner. The only reason why I said this was a good exercise is because this tells you how an induction motor actually works under the hood. Just using equations will not really give you much of an understanding of how a machine works. To be able to understand how a machine works, one needs to be able to go into these kind of diagrams and figure out how actually force is produced and how a motor will begin to rotate. That is extremely important. So, therefore, this particular method will be abandoned after this lecture, but I will just go through once again how this would work, because after all we've written some equations and it will be nice to bring it to a close. So, as always, before starting this lecture, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length online courses that you can find on my own website, which is pythonpowerelectronics.com. So this is the homepage of the project. It has almost all details that are related to this project. And if you go, there are these 4 buttons on the homepage, out of which if you click on Learn, it will take you to the list of courses. So as of now, I have 5 courses which are available on several MOOC platforms. The very first one is Simulating Power Electronic Circuits using Python. And in this, I talk about the basics of how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use Python and packages such as the SciPy package and the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python. In this course, I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power engineering applications. And the very last course I have is called Why Specialize in Power Electronics, and this is a free course targeted towards either junior undergraduate students or even high school students who have not yet chosen their domain of specialization. And the purpose of this course is to talk about some of the challenges and opportunities available in power electronics. So all these courses are available on two platforms, which is Decibels Labs and Udemy. If you click on any of these buttons, it will take you to the link for the course. The link for this page is available in the description of this video. So if you're interested, please do check out the description of this video. So with this, I will return back to my lecture. So as I said, this is where we were. We had actually calculated, or rather written, some equations on how we can calculate the force. So we had written several. For example, we had said that we can express the force as the magnetic field strength multiplied by the current multiplied by the length of the rotor bars. Right? And the actual force is equal to the force multiplied by the sine of angle between the magnetic field and the current. And we saw that in the case of an induction motor, at least in the ideal case, we saw that this phi is almost 90 degrees. Right? So therefore phi actual is equal to the actual phi produced. That is, we saw that it is tangential to the rotor. Therefore, this actual force is equal to the force which is produced were the magnetic field strength and the current at 90 degrees to each other. And then of course we saw that there is a torque which is produced. This torque is produced by the multiplication of the force and the radius, and of course the number of rotor bars, because a force is produced on each and every rotor bar, and we have several of them, right? So this is the number of rotor bars. So now of course it comes to calculation of this or at least the force, because we saw that there is a magnetic field strength. So therefore I came up with this equation, and therefore we can substitute this equation and get the total torque as here as well. Now once we get the torque, we now can solve this equation, okay? Because this equation here, that is omega m integral Te minus Tm divided by J, this is the mechanical equation, right? This is basically the equivalent, you can say the rotational equivalent of Newton's law of motion, right? Newton's law of motion is force into mass into acceleration, and this here is equal to torque is equal to moment of inertia multiplied by acceleration. So therefore with this, and therefore mechanical torque here depends upon the nature of the load connected to the induction motor. So for example, we can have several types of load. We can have linear load, we can have constant load, we can have quadratic load, we can have several types of load. You have basically, depending on the nature of what it is that is connected to the motor, you do have an idea of the kind of mechanical load which is available. So for example, we can say that Tm is constant with respect to, so I'll just say constant with respect to mechanical speed, right? So we can say that this, or actually this is not constant, we can just say that it is a constant, right? So no matter how much the speed of the motor changes, the mechanical torque will always be the same. Of course, this is a fairly rare case, because usually as your load the speed changes, the torque will also change. We can also consider another case which is equal to K into omega m. So this is, you can say, almost a linear characteristic, which means the torque increases linearly with the speed. And we can also consider things like K into omega m square, right? So this is like a quadratic with respect to the speed. And there are many such equations, and they will all correspond to different types of loads, right? Again, it doesn't really matter, because we are looking at the motor. We don't really care about what load has been driven, at least not right now. Later on, when we actually, if we get to the stage where we model an electric vehicle, then in that case we do have to come up with a reasonable model for the torque which is produced when the electric vehicle accelerates and as it attains a certain speed. But we are nowhere near that now, so it doesn't really matter. So once we do have this, and let's say we take the simplest case and we assume it to be a constant, in that case we can calculate this equation by just putting this torque, that is this here, is the electrical torque into this equation. So this gives us omega m. And of course, once we have omega m, we can come back here and put it in these equations. So for example, we've already said there are several equations which we have written, out of which there are a few which are dependent on the mechanical angle. So we have seen that LS and LR are independent. Right? This is a discussion which I had long back. If you're interested, if you're not sure, please do go back to it. So we saw already that for a cylindrical motor, RS, RR, that is rotor resistance, stator inductance and rotor inductance are all independent of the mechanical angle. Only the mutual inductance between the stator and the rotor is dependent on the rotor angle. And we had come here and we had said that this is the equation. That is, if we say that this is the mutual inductance between the stator and rotor can be expressed as some maximum value, then it is a cosine of the mechanical angle. And the maximum value is nothing but described again in a very similar manner as here. That is, we just have to find out that a certain current is flowing through the stator. This current will encounter a certain reluctance and therefore will end up producing a certain flux. Right? So this derivation I had done long back. So all again, once we have to take this equation, put it here, and now we have a set of equations. So we have several equations here. So we have 1, 2, 3, 4, 5, 6, and we have the seventh one, which is the equation of the speed. And all together we have several equations as well, right? So we have all these equations, and at the same time we have the seventh equation, which is the mechanical speed. So with all these, we now can solve this and actually build a simulation model. Assuming here, of course, that we do want to go in for this method of taking all the construction details into account, if we want to do that. Now, this is how we would end up closing the loop. Now the question here again is, we do not want to use this method, and this is something I already talked about. We don't want to use this method. So therefore, let's again say, let me call this construction details, and let me start a new page. So in this page, I'm going to talk about what we're going to do, which is different. I will just start this because it's a pretty long discussion that again we'll have. So how would we go about creating a similar simulation model, but without the knowledge of the construction details? This is the question which needs to be asked. So the first thing which we need to do is we need to come up with an equation for the torque, right? So let's start with this, that is the equation for the torque, because that is where we found out that there is a huge component of this construction details. So let us see how we can replace this first, and then let's write all the other equations. It is actually, many of the other equations are actually the same, right? Because these are equations that relate to any electrical system. It's not very different. So coming over here, so how would we do so? We use the law of energy conservation. And this essentially means that the input energy is equal to the output energy plus energy which is stored plus energy which is lost. So basically this goes down to the very simple definition that energy can neither be created nor destroyed. Energy can only be converted from one form to another. What we have as input energy is electrical energy, at least in the case of an induction motor, right? If it was a generator, then of course the input energy is mechanical energy, but for a motor it is electrical energy. The output energy is mechanical energy. And let me just leave this energy stored for, and the energy lost is of course of several types. So for example, we have electrical losses and we have mechanical losses. And we also have a few other types of losses which I'll talk about soon. Now, the reason why I want to talk about all this soon is that it all comes down to the magnetic field. A magnetic field is absolutely essential in the case of an induction motor. The reason, as we have already seen, is the induction motor is an electromagnetic machine in which this magnetic field plays the role of the medium for exchange of energy from the stator to the rotor. Right? And this is something we've seen over and over again. Why? Because we are only energizing the stator, at least in the case of a squirrel cage induction motor. This energization of the stator produces a magnetic field, which in turn induces an EMF in the rotor, causing a current to flow in the rotor bars, and this interaction between the magnetic field produced by the rotor bars and the magnetic field produced by the stator is what results in the torque which is produced. So this magnetic field is absolutely essential to the induction motor. Now, once you have a magnetic field, you however have certain other things that happen. A magnetic field always has stored energy. For that matter, even an electric field will always have stored energy. Any field typically stores energy. Now, besides the stored energy, there will also be magnetic losses. And these magnetic losses are hysteresis losses, plus eddy current losses, and maybe a few other types of losses which even I don't really know, because magnetism is a very specialized line, right? This is how much I know. So therefore, this stored energy has to be accounted here in the energy stored. So let me come back here and write here energy stored in the magnetic field. And here we come to magnetic losses. Alright. So this is a pretty big one actually. Let me just zoom out a little. Okay. So this, as you can see, is the entire equation. That is, input energy, electrical energy, is equal to mechanical energy plus the energy stored in the magnetic field plus the total losses. Right. Now, we can say that out of all these losses, some are significant, some are insignificant, right? For example, the magnetic losses are usually insignificant unless you have a really old motor in which the lamination has almost broken down, or some other issues have happened because of which the magnetic field is really messed up. You typically have magnetic losses which are very minimal as compared to mechanical and electrical losses. In terms of mechanical losses also, one can say that they are usually much lower than electrical losses, and also electrical losses can be expressed in such a way that they actually also represent mechanical losses and magnetic losses, right? And we'll talk about that soon. But what is important here is this equation now is independent, or rather, at least for now, is independent of the construction details, right? We are talking about the electrical energy, which we know is voltage multiplied by current. Mechanical energy is what is produced at the output, and this energy is stored in the magnetic field, and these losses have to be represented in some way. But now if you look, we are looking more at an abstract representation. We are not going into the details of the motor, right? Or rather, we have to find a way to avoid going into the details of the motor. So this will be our basis going further in deriving a new equation for the torque. So I will stop this lecture now because it's already gotten pretty long. If you have any doubts, please do post either in the comments or send me a message or email me, whichever is your preference. Otherwise, in the next week we will continue and try to start writing some equations using this so that we can actually come up with a final equation for the torque which is produced. So, thank you so much for listening, and goodbye for now.